Hello, I'm Kyle Kirkpatrick, and today I'm recording the reverberation of my apartment's parking garage. The recorded reverb can be utilized in audio production software as an effect that makes your audio sound as though it has been recorded in that space. This is accomplished through a technique called convolution, where the reverb recording is convolved with an input signal, shaping it with the characteristics of the reverb recording. I'm going to go through the whole process and try out several techniques so we can figure out which one gets the best result. My goal is to use a minimal amount of equipment so I can find the simplest, most portable setup for recording reverb. This can be done both cheaply and easily, so you can do it too with simple recording equipment. The basic premise is simple. I excite the space with a broadband noise that covers as much of the audible frequency spectrum as possible. I record the result. The noise may need some cleanup or processing. I use a convolution reverb plugin to apply the shape of the reverberation to the input signal. The quality of the result will depend on the care I put into recording the reverberation. The absolute easiest way to accomplish this is with a field recorder and a balloon. Popping a balloon creates a very short, broadband noise. Notice that on the spectrum graph, it shows signal in most of the audible frequency range. This kind of short, broadband noise is called an impulse. When one sounds an impulse in a reverberant space, the sound will echo and ricochet off of every surface. Since the impulse is only the initial transient of the sound, all trailing noise is just reverberation. This is called the impulse response, or IR for short. Assuming the initial impulse contains noise at every audible frequency, then the response should accurately reflect the reverberant characteristics of the space. If the space absorbs sound at a particular frequency, then there will be less reverberation at that frequency band. If the space reflects sounds at a particular frequency, then there will be more reverberation at that particular frequency band. Unfortunately, though a balloon pop is a convenient approximation of an impulse noise, it isn't perfect. So I will try another technique to compare and see which one yields the most desirable result. There are other things that can produce an impulse noise. A gunshot, for instance from a starter pistol, creates a very loud impulse, as do many firecrackers. I don't particularly want to use firearms or explosives in my apartment's garage, and those would probably be too loud anyway. Also, I don't have any. Though, those would be convenient options if one is recording an impulse response outdoors or in a very large space where you need a very loud impulse to get a good signal-to-noise ratio. I could also play back an impulse from a loudspeaker, which is a slightly more desirable option. However, that didn't quite work out, and I'll explain why it didn't at the end of the video. The other option I'm going to test is a sine sweep. While an impulse creates noise at a broad range of frequencies all at once, it is also possible to play each frequency separately and record the response. It would be impossibly tedious to do each frequency in a discrete step, so I can accomplish this most easily by playing back a sine sweep that gradually changes pitch from low frequency to high frequency. To play back the sine sweep, I will need to use a loudspeaker and a playback source. Then, after I record the sine sweep in the reverberant space, I will need to process the audio to create a file where all of the frequencies play at the same time instead of a gradual sweep. Since the initial dry sine sweep is a known value, I can use an algorithm to compare the dry signal to the reverb recording to see what has changed. This process is called deconvolution. I will be using software to do the deconvolution process, and I will show a couple of accessible options for software you can use. Once the sine sweep recording is deconvolved, the output file will be an impulse response very similar to our balloon recording. The potential advantage of using a sine sweep is a more detailed and accurate image of the reverberant qualities of the space. Since the sine sweep projects each frequency at the same amplitude, the hope is that this has fewer discrepancies than an unpredictable balloon pop. I'm going to test this theory out by comparing the two methods. I'm also going to compare different length sine sweeps and deconvolution settings to see which one yields a more desirable result. Before I head to the garage, I want to set up my sine sweeps. The software I am using for deconvolution also has a function for generating sine sweeps. I'm going to use the inbuilt sine sweep generator to ensure my recordings are compatible with the deconvolver. In the past, I have used Ableton Live's utilities for generating impulse responses. You can get Ableton's Convolution Reverb and IR measurement device as Max for Live devices in the Max for Live Essentials pack. It is free for Ableton Live owners. Ableton's IR measurement device plays back a sine sweep while simultaneously recording the room's response using a microphone, and automatically deconvolves it into an impulse response. While this is generally a convenience, it won't work for the simple setup I'm trying to achieve with this field recording. To use this, I would need to run a very long microphone cable from my playback station to my recording station. I would also need to have a laptop running Ableton Live for the recording session and an audio interface for the laptop. Instead, I would like to generate sine sweeps before I go into the field so I can play them back on any device, including a little music player or cell phone. Then I can simply record the response on my field recorder, which will be quite far away from the playback speaker. So I've decided to try out Voxengo Deconvolver. This software has a free trial that has most of the functionality, but does not support batch processing. Using the software, I generate sine sweeps of 3 different lengths: 3 seconds, 30 seconds, and 60 seconds. For each length, I also generate sweeps with the fade option turned on, so I can compare the different settings. So 6 sweeps in total. The Voxengo manual says that the reverse technique can yield better results when using low signal-to-noise ratio recordings, such as room and field recordings, which is precisely what I'm doing. Apparently the fade option is ideal for the reverse technique, so I want to test this out as well. I output all sweeps at a sample rate of 96 kHz and a bit depth of 24 bits, and I will also be setting my field recorder to the same settings when I record the room. This exceeds the capabilities of my playback speaker and microphone, but I want my equipment to be the limiting factor and not my output or input settings. So now I have my test sweeps, but I have a problem. When I have finished recording, I'll need to line up my field recordings so that they start at the same time as my original dry sine sweeps. This would be no problem if I could start the playback and the recording at the same time. But I can't be in 2 places at once. I could simply try to line them up in an audio editor, but since the sine sweep does not have any abrupt transients, it will be difficult to do that accurately. Fortunately, I have an idea. I create an arrangement in my digital audio workstation to sequence out all of my sine sweeps. I'm using Ableton Live for this step, but one could use any DAW to set up their sequence. I first set the project to 60 beats per minute and 1/4 time so that the timeline grid represents seconds. At the very beginning of the sequence, I put a click sound that has a sharp transient. I can use this sound to line up the field recording with the original sequence. It's just like the clappers they use in film production. I add in a synth sound, as I'm hoping to compare the recording of the synth in the room to the original sound with the convolution reverb applied to see if I got a realistic result. I also add in a dry impulse generated from Ableton's IR measurement device as a comparison to the balloon method. Unfortunately, this didn't work, and I'll explain why at the end of the video. Then I add in each sine sweep to the sequence. I space out each of the events so there is 10 seconds of silence in between. I want to make sure there is ample time for the reverberations to ring out before the next event starts. I export the whole sequence as a WAV file, again at 96 kHz 24-bit, to maintain the fidelity. Now, to record all of my sine sweeps in the room, I can just let the field recorder run and press play once on my playback device. Everything's ready to go, so I'll grab my gear and head out. At the time of filming, we are currently practicing social distancing for the COVID-19 pandemic. As most businesses are locked down, the hotel that shares a parking garage with our apartment complex is closed. Much of the parking garage is empty, and since it is the middle of the night, no one is in the garage. There are lots of good places to record some reverb. But there are very few power outlets. To To record my sine sweeps, I will need to find a power source for my monitor speaker. I'm in luck though. One of the internal gates for the apartment residence uses a standard outlet. I just had to unplug that for a few minutes. For my playback speaker, I'm using one of my studio monitors. It's a Fluid Audio FX50. The frequency response of these speakers is rated from about 50 Hz to 22 kHz, so I know that I will miss out on some low-end response. I'm not too worried about it, as I don't generally need to or want to apply reverb to sub-bass sounds, at least in music production. My playback device is my Surface, but I could have used a phone or portable music player too. It's just connected by an 1/8 inch to 1/4 inch adapter, so the connection is unbalanced. As it is a short cable run, I'm unconcerned about noise introduced from the cable. And I didn't want to bring an audio interface, as I'm going for a minimal, portable setup. My field recorder is an older Zoom H4n, and I'm using it with an Audio-Technica BP4029 mid-side shotgun mic. The mid-side mic can record in such a way that you can derive a perfect mono signal or a stereo signal from its output, and you can adjust this in post-processing. You to look it up, as it is a fascinating subject. The preamps on this old H4n do not have a great signal-to-noise ratio, so that will be a bit of a limiting factor for this recording. The microphone has a rated frequency response of 40 Hz to 20 kHz, so it will exceed the speaker's ability to produce bass, but it likely will not capture all of the potential high-end detail. One could use any speaker and microphone to record their impulse response. A Bluetooth speaker and the built-in mics on the field recorder would work fine. Whatever devices are used will color the sound, changing the resulting impulse response to some extent. When my recorded reverb is applied to a sound, it will sound like that sound is being played out of my speaker and recorded with my microphone. So if I used a Bluetooth speaker, the resulting impulse response would make things sound like they are coming out of that Bluetooth speaker. With exception though. Generally, when using reverb, it is good to adjust the ratio between the clean, dry signal and the affected wet signal. The dry signal will have the full spectrum of sound, and the wet signal will be band limited by the recording process we used to record the impulse response. For music, the end result can still be quite aesthetically pleasing when you mix the wet and dry signals together. Band limiting reverb for music is quite common and has a desirable sound, albeit sometimes a bit unnatural. For sound design purposes, it may be more important to capture high-fidelity impulse responses, as you may want to accurately model the sound of a given space. Regardless, I don't think anyone should allow concerns about quality prevent them from attempting to record their own impulse responses. Even low-fidelity results can still be useful and unique tools for your production, and they still have greater complexity and character than some of the more simple reverb algorithms used in many plugins. So now I'm ready to record. I start recording on my field recorder and just let it run. Since I had been recording balloon pops as tests, I already have a gain setting configured that I think is appropriate for the volume and distance, and I feel confident that it won't clip. I walk over to my recording station and start playback of the sine sweep sequence. The whole thing takes about 5 minutes. The playback of the sine sweeps is actually quieter than the balloon pops, but the sustained high frequencies are piercing and painful to listen to, so I advise some ear protection. After the sine sweeps play, I pop a balloon from the same position as the speaker. My goal is to have a balloon pop that matches the sine sweeps, so we can directly compare the two techniques. I would record multiple takes, but I'm a little concerned that someone is going to wonder why there are aliens in the garage, and I didn't want to explain why I was unplugging things and doing weird science at 2 a.m. Though, recording some random samples is still a priority for me. Back to the lab to process the recordings. Bringing the recordings back to my computer, I want to try a few different noise reduction techniques to determine which way is the best way to process my reverb recordings. The garage, even in the middle of the night, has a lot of ambient noise. I do want to point out that noise filtering is not a necessary step to creating an impulse response. It can literally be as simple as just recording a balloon pop. I'm trying 3 approaches to noise reduction. 1. No noise reduction at all. 2. Spectral noise filtering before deconvolution. 3. Spectral noise filtering after deconvolution. So a little file management, then I can get to some of the noise filtering. I'm using Adobe Audition as my waveform editor. As I mentioned before, I used a mid-side mic, so I have to use a channel mixer to mix the mid and side signals into a left and right stereo mix. I also have to cut the balloon pop out of my sine sweep recording, since I recorded them all into one audio file. I then move on to working on the spectral noise reduction for the samples that will have noise filtering prior to deconvolution. When working with this many copies of the recordings, it's really important to stay organized and give everything descriptive file names. I play around with the settings in the spectral noise reduction device to configure a preset that would be ideal for reducing background noise while maintaining the reverb tails in the recording. If you are new to spectral noise filtering, this probably all looks a bit cryptic. The basic premise is that you scan a portion of your recording that only includes background noise. This establishes a base level for the noise gate. If the signal is below this threshold, then it will get attenuated. If a signal in a particular frequency band exceeds the threshold, then that band will be allowed to pass at full volume. I'm using the noise reduction device built into Adobe Audition, but there are many options for spectral noise reduction tools. Isotope RX Editor has a fantastic noise reduction tool that I think is a bit easier to use than Audition's, but it's an expensive option. There's a free and really simplistic tool included in Audacity that is probably the most accessible option. The Reefer device in Reaper is another good option. It's more advanced than Audacity's tool, but also has a steeper learning curve. The great thing about Reefer is it is included in the free Replugs VST pack, along with some other great plugins from Reaper. Everyone doing electronic audio production should get the Replugs pack. It's a great essential toolkit. Let me know in the comments if you would like me to do a tutorial on spectral noise reduction, or if you'd like me to make a video extrapolating on any of the other topics I bring up in this video. I configured the noise reduction to have a slow decay so that the reverb is maintained even after processing. It leaves more of the background noise, but that is a worthy compromise. We're here for the reverb. Once I figured out something that works, I save my preset because I will be using it several times. I can now go to the sine sweep sequence and apply my preset. I select a portion of the recording that is only background noise. I am careful to select a portion that doesn't include the sound of me shuffling about or other intermittent sounds. It works best when you only select a portion that has droning, monotonous background murmur. Shift-P captures the noise print. I deselect my noise selection and use Control-Shift-P to open the noise reduction dialog. I select my preset and apply it to the audio clip. There's some additional low-end noise I'd like to remove. Since this noise print will be focused on just these lower bands, I don't mind being a little more aggressive with my settings to cut out this noise. There's an unfortunate low-end noise at the end of the recording. Some sort of air conditioner or other building appliance had turned on during my sine sweep recording session. I can use the noise filter again to try to remove the portion that coincides with the sine sweep. In Audition, you can lasso select portions of the spectrum graph and perform edits directly to the graph, kind of like an image editor. I'll delete the rest of this unfortunate noise. Keep in mind, I kept unedited copies of all of the source files. I still normalized the files that don't have noise reduction to maintain a consistent volume across my various audio clips. While I'm in Audition, I also clean up my balloon pop samples. I'll show you my process on this sample. I zoom the amplitude of the waveform so that I can see the noise floor in the recording. Waveform editors like Audition or Isotope RX Editor allow you to zoom in on your waveform in ways that just aren't possible in a creative music workstation like Ableton Live. It is really a different sort of tool. I can see where the reverb signal becomes indistinguishable from the noise floor. I cut the file just after this point. I then apply a fade so that the file ends with silence. Now, I go to the beginning of the impulse and trim the section prior to the transient. Where to cut can be a difficult choice, as I do want the transient to be as close as possible to the beginning of the audio clip, but I don't want to destroy characteristic detail that precedes the transient. Realistically though, since this is a balloon pop, that preceding detail is maybe an undesirable characteristic of the balloon, and wouldn't necessarily be present in a mathematically perfect impulse. I opt to get as close to the start of the transient as I can without cutting off the slope up to the transient. I try to slice at a zero crossing, but since it is a stereo audio clip, the two channels won't usually have a zero crossing at exactly the same spot. So I apply a short fade to make sure the start of the audio clip is at silence. I don't want the clip to start with a wave in mid-cycle, as that would cause a clicker pop during playback. I have to do the same editing process to both the balloon samples without noise filtering and the ones with noise filtering. Once completed with my initial file cleanup, I go back to Ableton Live to line up my sine sweep sequence with the playlist I set up on the timeline. I have two audio tracks, the one without noise filtering and the one with noise filtering. I'm hitting a limitation of Live's waveform editing capability. I can't see the waveform in enough detail to really see where the transient is on my alignment click. Well, back to Audition to cut off the beginning of these samples. It's notably easier to find the beginning of the alignment click in the audio clip with noise reduction applied. Back in Ableton, I re-import the corrected sine sweep recordings. They don't align perfectly, and I'm more confident about the noise-reduced version, so I try to manually line up the waveforms of the two clips using the noise-reduced version as the guide. Once lined up, I can easily slice them on the grid. Instead of exporting the sine sweep clips individually, I can just crop the separated audio clips. This creates discrete samples in the project folder that I can then rename and reorganize as I see fit. This is faster than exporting, and it also doesn't re-render the files, so the quality shouldn't be altered in any way. And now finally I'm ready to deconvolve. To deconvolve the sine sweeps, I need to first load up the original dry sine sweep in Voxengo Deconvolver. I select the dry sine sweep that matches the sine sweep recordings that I want to deconvolve. I have two versions of every recorded sine sweep, one with spectral noise filtering and one without noise filtering. I run the process to export the deconvolved impulse responses. I will have to repeat this process for each different type of sine sweep. For the sine sweeps that had fades applied when I generated them from Voxengo, I am running the deconvolution process the normal way, and with the reverse technique setting applied. This way I can compare to see what difference, if any, the reverse technique makes. Let's fast forward through the rest of the deconvolution. Let's see how the impulse responses turned out. I return to Adobe Audition and load up all the impulse responses. Some of these turned out great. Seems like there is notably less bass than the balloon pops, but maybe that is because there is a better balance of high frequencies. Some of these have some obvious problems. Oh dear, some of these didn't turn out at all. I'll investigate that a little further and share what I think went wrong when we do the final comparison. Now that deconvolution is done, I'm going to apply spectral noise reduction to copies of the impulse responses so we can have another noise reduction method to compare. I unload the clips that already have noise reduction applied, as I will not be applying noise reduction to those again. Now the only open files are ones that haven't had noise reduction applied yet. Fortunately, there is space at the end of these files that does not have signal from the impulse response and only has the background noise. I select this portion of the file to capture my noise print. Again, Shift-P captures the noise print. Now I can deselect the noise section and press Ctrl-Shift-P to open the noise reduction dialog. I will again use the preset I created earlier. That sure has been useful. I'm glad I saved a preset. Once I have completed the noise reduction, I also trim the files. I shouldn't need to trim the beginning of the file, but since I did it for the balloon pops, I can't help myself and I do it to these impulse responses too. We'll be able to compare the difference to the sine sweeps that have no noise processing, as I did not cut those or apply any fades. For some of the problem files, the noise reduction helps mitigate the problem. For this one that seems to have sustained bass through the whole clip, the droning bass is included in the captured noise print. Then, it is filtered by the noise reduction process. This probably removed some of the bass signal from the impulse response, but we'll see if this is a noticeable problem when we test it in a Convolution Reverb plugin. I have applied these changes without saving at this point. My intention is to use the batch processing dialog in Adobe Audition to save all of the modified files with a tag appended to their file name. The tag I use is noise filter to show me that I applied a noise filter to these samples. While I have other files with noise filter in the file name, the order of the descriptions in my file names indicates the order that the file was processed. The DC tag is appended by Voxengo when you deconvolve the sine sweep. So, if the noise filter tag precedes the DC tag, then I did the noise processing before deconvolution. And if it comes after, I did the noise processing after deconvolution. I still have the files that do not have any noise filtering applied. With that, I have now set up all of the different tests. Let's find out which one sounds the best. Back in Ableton Live, I load in all of the different impulse responses to audio tracks in Session View. I'm organizing with 3 columns for the 3 different noise reduction techniques. There are also audio tracks for the balloon samples with and without noise filtering. I'm changing the colors of the impulse responses that didn't work. I can drag and drop the impulse responses onto Ableton's Convolution Reverb device. Now that Ableton's Convolution Reverb is looking at the directory where all the impulse responses are stored, I can also select different impulse responses by using the drop-down menu. Here's a demonstration of some of the different techniques applied as 100% wet reverb on a multi-sample piano patch. For another demonstration, here's the reverb applied on a synthesizer patch. For this patch, I used the fantastic Helm VST by Matt Teitel. It is open source and free to download with a pay-what-you-want option. Please go support this developer and support this admirable distribution method that enables this software to be accessible to everyone. Which one sounded the best to you? Here are my conclusions. The balloon method had a high signal-to-noise ratio, which resulted in less noise in the recordings. The balloon method also seemed to have a more pronounced low-end response. But the volume of the bass is not necessarily a benefit, as the loudness is relative to the gain applied to the sound file. What is desirable is an even frequency response, and it seems that the balloon samples were somewhat lacking in their high frequency response. When we compare to the sine sweep impulse responses, it is apparent that there is a more even frequency balance and a greater detail in the high frequencies. I attempted to boost the high end in the balloon recordings and use the equalized sample for convolution reverb. This did help to even out the frequency response, but it still doesn't compete with the amount of detail in the sine sweep impulse responses. Boosting the high end on the convolution reverb's equalizer did not result in a significantly different result than modifying the impulse response sample with EQ. Despite the deficiencies of the balloon technique, a balloon sample was my favorite of the recording session. In this case, it's all about the location and setup. I was not able to record a sine sweep at this location, as I did not have a power source available there. The portability of the balloon method allowed me to capture an impulse in the ideal location, which seems to be more important than getting the highest quality. This seems analogous to recording music. Capturing the best performance is generally more important than recording with the highest quality, though ideally you have both. When comparing the balloon pop and sine sweeps that were recorded in the same location, it is clear to me that the sine sweeps have the more desirable result. Even the 3-second sine sweeps have considerably more detail than the balloon impulse. The noise in the unfiltered samples is less of an issue than one would expect. Though when using an unfiltered impulse response in the convolution reverb, it was possible to get a buildup of the trailing noise when the incoming signal was reverberating a lot. I would in the future cut trailing noise off and apply a fade to the end of my unfiltered impulse responses. Ultimately, the noise was hard to notice when using the unfiltered samples, and they tended to have a very desirable frequency response. One can see why many convolution reverb recording guides suggest that you do not use noise filtering on your recorded reverbs. For the sweeps that yielded unusable impulse responses, there was little improvement when noise filtering was applied prior to deconvolution. It did seem to mitigate some of the unintended noise in the usable sweeps, and it didn't ruin the frequency response. In my opinion, using noise reduction after deconvolution yielded a better result. Two samples that were unusable with the other two methods had a usable result with the noise filtering applied at the end. There was only one sample that was not usable, and I didn't even try to apply noise filtering to it because it was so bad. Voxengo's reverse technique had a considerable effect on the amount of noise in the recordings. Some of the sine sweeps with the fade in and out setting applied failed to make a usable impulse response using the normal technique, but those same sweeps yielded a very good response when using the reverse technique. It seems to have mitigated the unintended noises that caused the deconvolution to fail. It is also notable that the shorter sweeps tended to have fewer errors in the recording, which resulted in fewer of the samples failing deconvolution. The 30-second sweeps had a noticeable improvement in quality over the 3-second sweeps, but there seems to be diminishing returns with the 60-second sweeps. The failure rate of the 60-second sweeps was higher, and it would seem that it is largely due to the increased likelihood of having unintended noises captured in such a long recording. So, in the end, I think my preferred sweep is the 30-second sweep, at least for this location. The reverse technique seems like the best option for mitigating extraneous noise in the recording. Applying spectral noise reduction after deconvolution had consistently better results than doing the noise reduction prior to deconvolution. Cleaning up noise in the files before deconvolution had about the same number of failures as not doing any filtering, but the reverse technique did save impulses that otherwise failed. It does seem like a good idea to trim and apply fades to your impulse responses, even if not employing any noise reduction. For future impulse responses, I will continue to record a sequence of various length sine sweeps. This method allowed me to run the recorder and the playback asynchronously, and it gave me multiple takes to choose from. Realigning the recording in post-production was quite manageable with the alignment click. I will continue to record balloon pops at most locations, and I will record sine sweeps when there are favorable conditions for this technique. I'm going to have to invest in a battery pack that can run my studio monitor or a battery-powered speaker. Let's talk about the failures. The impulse I placed in the playback sequence did not work. An idealized theoretical impulse noise should be an infinitesimally short, maximum energy spike. The one generated by the Ableton IR measurement device is a very short blip that is like the sum of one cycle of every frequency that can be reproduced in the sample rate the engine is currently running at. If you look at it on a spectrum graph, it just looks like a solid line through all of the frequencies. If you look at it on the amplitude graph, it's a wavy line with a peak in the middle. In a closed electronic system, this could excite the delay or reverb in a hardware unit to elicit an impulse response. In my speaker setup, there were a couple problems with playing back this impulse. For one, I should have normalized it to the maximum amplitude possible. As it was playing back too quietly. I really need to play it back extremely loudly for it to excite the space. My speaker may not be capable of playing it back loud enough, and there is risk of damaging my studio monitor. I can't imagine it is good to make my speaker pop like a balloon at maximum volume. The other issue is that it is so short my speaker may not be responsive enough to play it back accurately. I could have done this differently. The goal is to play back signal at all frequencies simultaneously. I could have had a very loud white noise playback for a short time. I would want it to be longer than a single cycle of the waves, as I want to accommodate the responsiveness of my speaker. Also, white noise is randomized noise across the whole frequency spectrum, but it doesn't play all frequencies at the exact same time. I would have to find a compromise between keeping it short, as an impulse would be, and playing it long enough to hopefully cover the whole frequency spectrum. Perhaps I could play the white noise for any length of time, and then abruptly stop. The trailing reverb would be the impulse response. I could cut the white noise signal from the recording and only keep the trailing reverb. This should certainly be an experiment to try next time I am testing reverb recording methods. For the sine sweeps that failed the deconvolution process, I can only explain this as the algorithm interpreting extraneous noise in the recording as reflections of the sine sweep signal. If there is any amount of noise in a given frequency band after the playback of the sine sweep, the algorithm is going to treat it as an echo of the initial signal. I did check my files and run the deconvolution again, but it had the same result. This was during the portion of the recording that had the air conditioner noise in the background. Apparently, the spectral noise reduction was not sufficient to mitigate the problems this noise introduced. I mentioned earlier in the video that I included a synth sound in the sweep sequence so I could compare the dry synth sound with the garage recording and the convolution reverb. The sound I picked was too short and played back too quietly to give a meaningful demonstration. Next time I do this, I will use a louder, longer musical sample instead of a one-hit. Thank you for watching my reverb recording experiment. I hope you learned something along the way. I certainly did. Making audio production instructional videos is a new thing for me, so I'd appreciate your feedback. What should I include in the next video? What topics would you like me to cover in the future? Check out the video description below for links to tools that I used in this video. I will also have the impulse responses from this recording session available for download, so you can try them out in your own productions. You do not need the Ableton Convolution Reverb device to use these impulse responses. They will work in many Convolution Reverb plugins. I will put a link to a free Convolution Reverb plugin in the description below.